Okay.
Okay. So again, it's a great pleasure to present Kuo-Chang Chen. We know since quite a long time, because since he was still a student of Frick, and we started having exchange of mails. And then we met in many places, in Taiwan, in Paris, in Beijing. I even attended his wedding party, which is a great memory. So it's a real pleasure to see he became a master of in particular, the variational method applied to n-body problem. And today he will essentially speak on the n-center problem, if I understand, by variational methods. So I'm very eager to hear his new results. So please, Kuo-Chang.
Thank you. Thanks, Alan, for the introduction, and thanks for the invitation. It's my pleasure to give a talk here. I will put more emphasis on my recent work, especially on my collaboration with Guowei Yu about the n-center problem, and some progress that I made during the 3 weeks quarantine in hotel. I will briefly outline the ideas and the results. Okay, let me begin with I think the topics. Many of the audience are already familiar with to some degree. So I will be brief on the introductory part. Let me begin with a fundamental question about the existence of the n-body problem. Consider the planar n-body problem. One of the fundamental questions is determine the existence of periodic solutions within a topological class of loops. The topological class can be in different sense. For example, if we consider the masses in a complex plane or R2, and let Mi be the masses, the topological class can be determined by the homology class. For example, if we determine if we are given some prescribed winding numbers of those xi minus xj, that's equivalent to giving a fixed homology class. Or we can also fix a homology class. For example, if we consider the configuration space with collision sets removed, then we can consider any element in the free homology class. Or we can also consider similar classification, topological classification in the reduced space, with the rotation quotient out. For example, the famous one, the three-body problem. The three-body problem, if we consider those triangles formed by the three bodies and the class of similarities, all similarity classes form a triangle, which is known as the collection of triangles forms the shape sphere. This is a picture from Rick Moko's paper in 1988. I think it is a quite famous picture. If we consider the sphere, the collinear configuration corresponds to the equator, and the north pole, south pole are the Lagrange equilateral triangle. And the upper hemisphere represents the positively oriented triangle, and lower hemisphere represents the negatively oriented triangles. And on the equator, there are three spatial positions corresponding to double collisions, where we have like 1, 3, 2, 3, and 1, 2. Those three are collision configurations on the shape sphere. If we remove those collision configuration from the shape sphere, then we have a sphere with 3 points removed. So topologically, it is equivalent to R2 plane with two halls. So its homology, first homology group is just a free group with 2 generators. And we can ask about the existence of certain orbits within the free homology class. For example, if we consider the blue loop, this corresponds to prograde or retrograde orbits, because we have quotient out rotations. Okay, in this picture, we can also talk about existence of shape space figure 8, an orbit which looks like figure 8 orbit on the shape sphere. But we could also ask whether there are solutions which is really the figure 8 orbit found by Alan and Richard Montgomery in 2000. This is a very, very famous example where for this orbit, if we project that down to the shape sphere, it goes like the blue curve. It goes up and down along the equator. Of course, there are many more topological classes we can talk about. For example, it's, like this blue curve. Then if we look at this blue curve, we can classify them according to the syzygy sequence they produce. By syzygy, we mean collinear configuration. So if we look at the orbit, it passes through the equator multiple times. If it goes from left to right, it goes from the one collinear configuration, one syzygy, to another type of syzygy, and then to the third syzygy, and then it forms a sequence which we call the syzygy sequence. There are 2-3 recent papers by Rick Moko, Richard Montgomery, and Venturelli about realizing syzygies for the three-body problem. And today I'm going to be focusing on a variational approach for this problem. Now, for the variational setting, it's very quite standard. It's just let K be the kinetic energy and U be the potential, and L be the Lagrangian, which is the kinetic energy plus the potential part. And we consider the action functional, defined as the integration of the Lagrangian from some T0 to T1. And in a suitable function space, usually we choose the space H1. This action functional has its Euler-Lagrange equation is exactly the equation of motion for the embodied problem. So it is quite natural to tackle the embodied problem from variational perspective by looking for critical points for the action functional in suitable function spaces. Now, suppose we want to look for a particular solution, for example, within a particular symmetry type or particular topological type, and we just let the function space be omega, be the space of paths or loops in that function space. And then we consider the minimization of the action functional on the weak closure of this function space. Then, of course, the problem is the minimizing the variational approach is to find critical points of the action functional within this symmetry class or topological class within the interior. Then there are two natural problems that we have to tackle. The first one is the compactness. Of course, first we need to make sure that the existence of the minimizer. Usually this is carried out by weak lower, checking the weak lower semi-continuity, which is by now is very standard. Basically the consequence of Fatou's lemma and weak lower semi-continuity of H1 known, and in general known. And the other one is to check coercivity. Coercivity of the action functional is usually carried out by some Bangaré type inequality. This part is quite standard by now. It appears in many research papers with more or less the same proof. That's about the compactness. The second part to take care of is the regularity. Regularity is to determine the minimizer, knowing the existence of minimizer. Then the problem is to determine whether the minimizer has collision or not. And this is usually carried out by either using global estimates or local deformation arguments. Now I'm going to briefly introduce the global estimate and local deformation arguments. The strategies for solving the regularity part. The first is by global estimate. The global estimate, the idea is quite simple. It's just that we choose a function space. Then we try to find a good lower bound estimate for the action values among paths on the boundary of that function space. The boundary consists of contains paths with collisions. And then after we find this lower bound, we want to find an even better test path in the function space with even lower action value. If successful, then we can conclude that the action functional the infimum is attained in the interior of the function space omega. So that's the idea. The idea is quite simple. The second argument is about is a local deformation argument. The local deformation argument, the idea is to blow up the collision path. Around the collision, we just scale it, and blow it up, and scale it to a rectilinear parabolic path. And locally, we want to deform that rectilinear path to another path with lower action value. This has been used in many works, Marshall, Chenciner, Venturelli, and many others. And that this is also a quite well-developed methodology for solving regularity. There are many works, many progress since the discovery of the figure 8. Actually, my list is, of course, not complete. Actually, I have a kind of sort of lost track of new results in this direction. But anyway, there are many progress. By now, it becomes quite clearer and clearer how we can use variational methods, have some symmetry constraints to play with some symmetry constraints, basically based on Ballet's principle, to produce new or to construct solutions for the embodied problem using variational approach. But an important part is that we need some symmetry to play with. If we only have topological constraint, then the story is different. It can be traced back to a note by Poincaré in 1896, where he essentially imposed some homological constraints. And he also observed that the action value of a collision path could be about the same action value as a loop without collision. So it's difficult to tell whether minimizer is going to have a collision or not. And this has been studied again by William Gordon in 1977, which is very famous work. He actually showed that if we consider those H1 loops around in a space of paths which goes around the origin, which winds around the origin at least once, among this function space, the action minimizers are precisely T-periodic H1 T-periodic Cabralian orbits and collision ejection orbits. So collision ejection orbits and those elliptic Cabralian orbits, they all have the same action value. So from that point of view, the minimizing method does not discriminate those paths with collisions, because their action value could be just about the same as those non-collision ones, even circular ones. And Andrea Venturelli has another paper about the three-body problem, basically imposing the homological constraint, and show that either we are going to have Lagrange homographic solution or collision solution, or minimizer do not exist. So in some sense, it tells us that we do not really get something new if we just impose some purely topological constraint. And I have another work which requires some reflection symmetry, but there's no constraint on the masses, on equal masses, about constructing retrograde orbits for the three-body problem. Well, if we compare topological constraints and symmetry constraints, then we can see that in the past 2 decades, there are relatively few results on minimizing method with purely topological constraints. Why? There are some major difficulties when we consider the minimization problem with purely topological constraints. The major difficulties are, first, if we consider minimizer on the weak closure of a topological class, usually minimizers have collisions. It's just like the results I just mentioned about Venturelli. Usually, what we get are really solutions with collisions. So in that sense, the global estimate doesn't work. And secondly, from the perspective of local deformation argument, in general, if we consider local deformation argument locally at a collision, we cannot deform the path to the function space we are given at the first place. So local deformation argument doesn't work. Also doesn't work in general. So that's the main difficulty. Both global estimates and local deformation arguments are problematic for problems with purely topological constraints. So now the strategy of developing this approach to the embodied problem becomes we begin with kind of toy model, the simplest model. A toy model for the embodied problem is the n-center problem. Then we step a little bit forward to the restricted problem, and then to the embodied problem. So that's the strategy. We begin with the simplest model. So that's what I'm going to focus on, the n-center problem. And actually, I think that's the main inspiration for studying the n-center problem from variational perspective. Now, the n-center problem is the very much simplified version of the embodied problem, where all masses are fixed except one. Okay, only one body is moving, and the remaining bodies are fixed in space. Those fixed bodies are called centers. And consider n centers with positions Ci, and the masses are Mi or mu I. The free particle, we assume the free particle has unit mass, and let Z be the position. Then the equation of motion is very much like the equation of motion for the embodied problem. Okay. As we can see, the acceleration of the free particle is the force acting upon the free particle is the sum of the forces due to all those masses, due to those centers. It's very much like the embodied problem. And the potential and the Hamiltonian and Lagrangian are all similar. And of course, the action functional also. The action functional is just an integration of a Lagrangian. Now we have only one particle moving, so the kinetic part is particularly simple. It's only one term, half of z dot squared. Okay. But pretty much everything is the same as the embodied problem. It's just that we consider the action functional is the integration of this Lagrangian, this new Lagrangian. We integrate that over the time interval from 0 to t. And the equation of motion for the n-center problem is precisely the Euler-Lagrange equation for this action functional. Now, this is a very classic problem, the n-center problem, where if we have only one center, that's precisely the Kepler problem. For the case, we have if we have two centers, it is also known as Euler's three-body problem. We call them call it Euler's three-body problem because it first appeared in Euler's memoir in 1760, but it later attracted attention of Lagrange, Legendre, Jacobi, Carrier, Whittaker, and so on. Many people have attracted have worked on this model, or maybe use this model for various kind of problems. But what I would also like to mention that's very closely related to what I'm going to present today is about the syzygy sequences. As I just mentioned, syzygy means a collinear configuration. Now, if we have two centers on the plane, then the free particle may just become collinear with the other two centers. So there are basically just three kinds of syzygies. And if we consider the sequence of syzygies, we just record all the possible syzygies, then it forms a syzygy sequence. And recent work by Doolin and Chenciner-Montgomery in the 2016, they classify all possible syzygy sequences. This is a integrable system, so it's possible to classify all of the possible syzygy sequences. And for n greater than or equal to 3, the system becomes non-integrable. And if the energy is positive, then the topological entropy is positive for the spatial problem. And there are chaotic invariant sets. It has been intensively studied by Bolton, Negrini, Klein, Knopf, and so on. Okay. That's what I call classic results, which is not from the variational approach I'm going to talk about today. Now, let's talk about the variational approach. The variational approach to this problem, as I just mentioned, is very much inspired by the developments of the variational approach to the embodied problem, especially for the problem with topological constraints, because we have some obstacles that two main difficulties I just mentioned. So people start to work on the simplest model, the n-center problem, and impose some purely topological constraint and see what happened. And it was done by Terracini in 2012 and Castelli 2009, and Guowei Yu, and I have another work with Guowei Yu. My joint work with Guowei Yu also studied a special case where we have collinear centers. And roughly speaking, what we can do is that we can show existence of classical solutions which look like the loops that we can see from the, or not necessarily loops, those paths, like what we see on the picture on the right. For example, the first one, the one on the top, there's a loop which encloses 3 centers. If we enclose several centers, at least 3 centers, then no problem. Such a solution, classical solution, exists. And the one below is that there might be some loop which enclose only 2 centers, but if we have a non-simple closed curve, and there are other loops which enclose 2 or 3 or more centers, then that's also an allowable topological class. For such topological classes, we can be sure that there are really classical solutions which realize such kind of which really falls in such kind of topological class. Okay. Now let me briefly explain why we have this kind of constraint. Let me first mention other results. Those results I just mentioned have the constraint that we need to have at least 3 centers. But how about the case 2 centers? It turns out the 2 centers case, the case of 2 centers is difficult. Okay, I'm going to briefly outline how we can deal with the 2-center problem from variational perspective, especially the lemniscate and plenary type solutions. Numerically, the solutions like the picture on the right. Okay, now let me briefly describe the idea of proof. Basically, we impose the topological constraint using syzygy sequence. Now, consider a simple model. This is in my joint work with Guowei Yu. We consider collinear centers on the real line, and let those centers be C1, C2 from left to right, C1, C2 up to Cn. And we can split the real line into several intervals. If we just let C0 be minus infinity and Cn plus 1 to be positive infinity, then although Ci minus 1 to Ci is an interval, we let it be the ith interval. And so we have I plus 1 intervals. And whenever the free particle passes through some of those intervals, then we have a syzygy. And there are n plus 1 type kind of syzygies. So if we have a path which passes from one syzygy to another, and then to another, then to another, then we have a sequence of syzygies. And that's what we mean by a syzygy sequence. So a syzygy sequence is a sequence of symbols S1 to SL, where each Si is from 1 to n plus 1. And we impose a condition that 2 consecutive Si are different. That's what we mean by a syzygy sequence. Now we say a syzygy sequence is realized by a collision-free path if we can find an increasing sequence of times, T1, T2 up to TL, such that at the moment Ti, the free particle is exactly at the interval I sub Si, okay, the Si subinterval, okay, and other than those moments, T1 to TL, other than those moments, we do not have syzygy, okay. In this case, we say the syzygy sequence S is realized by the collision-free path Z. For example, if we look at a picture here, it starts from the leftmost interval, that's the first interval, and then to the third interval, and then to the fifth, and then back to the second, and then to the sixth. So it realizes the syzygy sequence 1, 3, 5 to 6. Okay, but for this path, we can extend it periodically by reflecting it with respect to a real line. Then we get a path which realizes the syzygy sequence 1, 3, 5, 2, 6, 2, 5, 3, 1. Okay, so I think it's a quite intuitive way of giving a topological condition on the path space. We can easily extend the idea to bi-infinite syzygy sequences. We can consider bi-infinite syzygy sequences. We say a bi-infinite syzygy sequence is realized by a collision-free path Z if we can find a bi-infinite sequence of time, increasing sequence of time, Ti, such that it satisfies exactly the condition we just described. Okay, so from this, using this terminology, we can talk about globally defined solution which realize some bi-infinite sequence, bi-infinite syzygy sequence. Now, suppose we are given a syzygy sequence S. We let the space of paths which goes up and down, keep every time it becomes a syzygy, it goes from either upper half plane to lower half plane, or from the lower half plane to upper half plane. Collect those paths, and we denote the path by omega S. Here is a theorem that I have with Guowei, published in 2018. So I call it Theorem 3 because it's about 3 centers. Okay, it's only 3 centers, precisely 3 centers. If we consider the 3-center problem where we have the 3 centers along the real line, the collinear 3 centers, then there is an interesting connection about the realizable syzygy sequences with the Fibonacci sequence. If we let Fm be the Fibonacci sequence, and we fix any time, fix any transfer time t, and we are given any positive integer L, there are at least not exactly at least F sub L plus 2 minus 2 syzygy sequences of length L for this 3-center problem, which can be realized by collision-free solutions, and these solutions are minimizers of the action functional, of course confined to the space with that prescribed syzygy. Okay, so there is a very I think it's a quite intriguing connection between realizable syzygy sequences and Fibonacci sequence. And we can generalize this kind of counting the number, the list, or counting the number of realizable syzygy sequences. We can get a lower bound. Generalize this kind of counting. For general n, we have this lower bound. Actually, we can improve that, but it's a relatively simple lower bound estimate for the case of collinear centers. We can count the number of realizable syzygy sequences. Realizable means that realized by some classical solution. So that's a step toward the problem of solving the classical solution with topological constraints. And another, what was in the proof of this kind of theorem, of this kind of finding, this kind of formula, one very important part is about collision avoidance. The collision avoidance is based on some collision reflection principle, which roughly speaking that if we have a minimizer which hits some center, has collision, and it bounces back exactly the way it came from, that's the incoming angle and the outgoing angle are exactly the same, then because of the minimizing property, they are going to have the same energy. So it's going to be symmetric. So it's going to be a collision reflection solution. That's a collision reflection principle, and also uses some minimizing property of Cabralian orbits, which essentially says that if we have a minimizing path, then if its incoming angle and the outgoing angle are different, if these two angles are different, then we can locally deform it in a direct way or indirect way, both ways, to lower the action value and get a contradiction. So the case that we cannot exclude is exactly the case that is collision reflection path. That's the incoming angle and outgoing angles are exactly the same. That's the case that we have to deal with. And that's pretty much the reason why those previous results have the restriction on at least 3 centers. Because for the 2 centers, it might be it might be the case that the minimizing path is a collision reflection path that bounces back and forth between 2 centers. And for the local deformation argument, in general, we cannot exclude the possibility of having this kind of path as the action minimizer. We have another work about the construction of chaotic orbits. The chaotic orbits, including homoclinic and hyperclean orbits. This has been done by Bolton by using the very geometric approach for the regularized system. But we wonder if we can use variational approach to do the same thing. This is very much inspired by some work since 1988 and many other works in the 1990s by Rabinovich. Constructing chaotic orbits, there are basically 2 approaches. One is a geometric approach, which in principle we want to construct a horseshoe. And the other is variational approach, which is, as I mentioned, an approach by Rabinovich. Use a variational approach, and there are many applications of this approach to Hamiltonian system and PDEs in the 1990s by a lot of people, Bolton, Serre, and many more. And our approach is inspired by the approach of Rabinovich. So the idea is that instead of fixing the time, we consider free time minimizer. And instead of considering the original Lagrangian action functional, we consider shifted Lagrangian action functional. So we just call it LH, Lagrangian action functional. And some fact about free time minimizers. If we consider the shifted Lagrangian action functional, free time local minimizers are H energy solutions. So if we fix the energy, this is like we fix energy, we get a free time minimizer, or we fix time, and we the previous one is a fixed time minimizer, but now we consider free time minimizer. Then what we get is fixed energy solutions. And also, if we consider free time local minimizers for the action functional, among those paths which alternate between upper and lower half planes, as I just explained, it goes up and down. And if the energy H is non-negative, then the minimum, the free time minimizer, the minimizing the value of the action value of the free time minimizer is finite. This gamma H means the action value of the free time minimizer. And if we consider one particular case, if we consider at least 3 centers, let's just assume, for example, if we have 3 centers, and we consider the syzygy, which goes from, for example, 1 to 4, and then back to 1. Then we consider this kind of syzygy, and we consider free time minimizer among those paths that I just mentioned, the alternate between upper and lower half planes. Then we are going to get closed loops. It's not quite surprising, but that's what we need to use for our main results. Okay, now let me briefly explain our idea of getting a heteroclinear orbit. Now we consider bi-infinite syzygy sequences of this form. That is, it's eventually periodic in forward time and backward time. Before S0, it's just keep repeating R1, R2, R1, R2, R1, R2. And after Sm-1, it becomes R3, R4, R3, R4. It's eventually periodic in forward time and backward time. And those R1, R2, and R3, R4 satisfy the condition I just mentioned in the previous proposition. So if we just have bi-infinite syzygy sequence, that's exactly the periodic bi-infinite syzygy sequence, R1, R2, R1, R2, R1, R2, and so on. Then we get a loop. For example, that's R1, R2 is 1 and 4. Then we get a loop that just go to the first interval, to the fourth interval, and back to the first interval, then the fourth interval, and it's gonna be a periodic loop. And R3, R4 can be from the second interval to the fifth interval, and so on. Now, this is our main results about the chaotic orbit. Our main result is that if we fix a non-negative energy, and we consider the case of collinear centers, the planar collinear n-center problem, and we consider a syzygy sequence which satisfy the condition I just mentioned. But actually, I have mentioned here is another condition, that's those adjacent syzygies are sufficiently separated. Actually, it's not a very complicated condition, but I just don't want to get into too much technical details. So let's just say those adjacent syzygies cannot be too close. Okay, then in this case, we can get homoclinic or heteroclinic orbit for the n-center problem. It is heteroclinic if the R1, R2 are different from R3, R4. Okay. Basically, the idea, let me show 2 pictures to explain the idea. For the picture on the left, we can see that there are 2 loops. One loop that goes around 2 and 5, 2, 5, 2, 5, 2, 5, and there's another loop that goes around 3, 6, 3, 6, 3, 6, and the path that realizes the bi-infinite sequence 2, 5, 2, 5, 2, 5, and then at some moment it transferred to switch to 3, 6. It's like the solid curve. The solid curve originally in backward time is asymptotic to the 2, 5, the 2, 5 ellipse. And in forward time, it's approaching another ellipse. And not really ellipse. It's just like an ellipse. Okay. So what we have done is to construct this sort of orbit by variational argument. And the picture on the right is from 2, 5, 2, 5, 2, 5, and it switches to an interval, the number 7, and then back to 3, 6, and then repeat around 3, 6. That's another kind of heteroclinic orbits. So these 2 pictures shows what kind of orbits we are getting from the theorem. And I would, in order to talk about the 2-center problem, I would like to skip the idea of proof. But roughly speaking, is to consider some modified, normalized action functional, which is defined on the whole on the path of H1, not H1 loops, but H1 local path. And the idea is very much like the work by Rabinovich in the 1990s, and we consider those normalized action functional. You see, the normalized action functional. First one, the integration of shifted Lagrangian minus the minimum value among those loops that goes around R2, R1, minus the minimum action value. And in forward time also do the same thing. And we just add them up and then consider the minimization. The rest of the argument is very much like the work of Rabinovich. Okay, now let's move on to the two-center problem. What's wrong with the two-center problem? We can't, or why can't the previous approaches be applied to the case of n equals 2? As I just mentioned, the problem is that if we are dealing with a loop with some topological condition that some of the loop enclose two centers or one center, just like the first two pictures, then from the collision reflection principle, we cannot exclude the case of collision reflection path of the ejection collision loop on the right to be action minimizer. We cannot distinguish them from action minimizers in general. And that also explains why we need at least 3 centers in order to apply variational approach when we are imposing some purely topological constraints. Okay, now I'm going to explain how I can handle this case using variational method. Now let's consider these two topological classes by imposing the CSG constraint. For example, now I'm letting the interval on the left to be W0, so the CSG sequence becomes from symbols from 0, 1, or 2. Okay, and then if we look at the picture on the left, it is like a theme-shaped curve. If we just extend it periodically, it becomes a lemniscate or figure 8 type orbit, where the orbit, each lobe encloses only one center. And the picture on the right, if we extend that periodically, then we are going to get an oval, an ellipse. Well, that's precisely an ellipse. I will explain why. That's how it's precisely an ellipse, which encloses exactly 2 centers inside. So that's the 2 cases that's not included in previous approach with purely topological constraints. At the first, the picture on the left realizes the CSG sequence 0, 1, 2, and the other one realizes the sequence 0, 2. Here is the first main theorem about the two-center problem for the lemniscate type orbit. Here is a very simple condition. If the time, capital T, is greater than a threshold value which depends on the masses of the centers. Well, I fixed the position of the centers. One is at -1, one is at +1 on the real line. I fixed the position of the centers and let the masses of the centers be μ1, μ2. Then, if T is greater than this threshold value, which purely depends on the masses, then the minimization of problem of the action functional over the space of loops, the space of path, which I just showed, that goes from the 0th interval up to the first interval, and then goes down and goes back to the second interval. This kind of path in this function space, the action minimizers are collision-free. And if we extend that, then it becomes a 2T periodic solution of the lemniscate type. Okay. The picture on the left is for equal mass, equal centers, and the picture on the right is the bigger center is 0.8 and the smaller center is 0.2. The mass. The second result is about planetary type. The planetary type is another threshold value, and another threshold value. If T passes that threshold value, then the minimizing problem, the action minimizers are going to be classical solution, and they can be extended to 2T periodic solution of planetary type. Here I would like to I should mention classical result by the classic theorem about, called the Bonnet theorem in classical mechanics. From the Bonnet theorem, applied to the Euler's three-body problem, the two-center problem, then every ellipse with falsely C1 and C2 are the trajectory of some classical solution for the two-center problem. This is a result of a Bonnet theorem, a consequence of Bonnet theorem. So the existence part is not new. It's just like the Keplerian orbit obtained by William Golden is not new. The new part is about the minimizing property. What I show is that if t is greater than some threshold value, then those kind of elliptical orbits, they are indeed actually minimizers. Okay? Within the topological space, I just mentioned omega 0, 0, 2, a fixed CG sequence. Then the minimizing orbits are really those kind of elliptical Keplerian orbits. Now, lastly, let me briefly describe the idea. The idea is that using local deformation argument, we get a collision reflection principle. So we are dealing with what we have to deal with are exactly those rectilinear ejection collision solution, which moves along the real line. Because if they do not move along the real line, then those kind of collision with ejection orbit, they can be locally deformed to either to the left or to the right to lower the action value. The only case that we cannot reduce the action value by local deformation argument is the case where the particle is moving along the real line, which goes from the first center, ejects from the first center to the second center along the real line. And for this case, we can get a lower bound for this kind of ejection collision solution. The action value for this kind of collision ejection solution, which is the key point is the second term. That's the order t term. And now we want to choose a good test path. The idea is to consider two auxiliary Kepler problems. The two auxiliary problems, one is by Xi, the other is by eta. The one by Xi means that we put the two centers, move the second center to the first center, right? So that we have mu1 plus mu2 at the position of C1. And the second Kepler problem is moving both centers to the right, to the center C2. Okay, and then we consider Keplerian arcs, elliptical Keplerian arcs for these two Kepler problems. And one is the first arc is for the first Kepler problem, first auxiliary Kepler problem, which goes from W0 to the origin, and its axes are on W0, and another axis is exactly the origin. Okay, we consider this kind of Keplerian orbits. Of course, this that imposes some condition on the transfer time t according to the Kepler's third law. So that's a condition on the there must be some condition on the transfer time t in terms of the mu1 and mu2. And then we just combine this kind of path with another similar solution for the second auxiliary Kepler problem and concatenate these two curves to a semi-shaped curve within the topological class we are dealing with, and we can get some direct estimate and show that this concatenated test path has action value that is less than something of order t cube. Now remember that the other one we have order t term. So when t is large, then certainly the order t term is gonna dominate this term, this t cube term. So that explains how we can combine the local deformation argument with the global estimate argument for the two-center problem. And similar for the other case about planetary type. But actually this one we need some extra technical tools about complete elliptic integrals of the first kind. But I'm not going to explain that here. But we do need some more technical estimate for complete elliptic integrals to get another estimate for the suitable test path. And again, we have a term that's of order t cube. So using the same idea, we can get that when t is large enough, then the action value of this test path is going to be smaller than the bound we get, the lower bound we get for the ejection collision solution along the real line. So that's the main idea of my approach for the two-center problem. So that's it. That's the last slide that I do not understand. That's my last slide.
Thank you very much for a nice talk and full of results. So probably there will be any questions. So if there are questions, please.
Hello, Alain. Hello, Kuo-Chang. Yes, just a little comment, an anecdotic about, you mentioned Legendre at the beginning, that there are figures in Legendre book in the end. It's a book 1884, I think, or 88, 34 or 38. And the figure, in the figure there is a figure 8 orbit, not symmetric, but it's doing like this. And there is also a break orbit on the two fixed center problem. Two fixed center problem is showing a figure 8. It's showing a break orbit. It's showing also collision orbit. Maybe the first time historically where a collision, binary collision, was regularized. So maybe it's interesting for you.
You say that's Jacobi?
No, Legendre. Adrien Marie Legendre.
Let me know the reference. You said which year? I know it's
1834.
Oh, 1834. Okay.
The one you mentioned, probably. I can show you even the figures if you give me the.
Okay. I've seen because I saw a lot of numerical figures in during Montgomery's paper. I know there are already a lot of numerical figures available, so I did not talk about that part. But certainly I didn't do the historical research on who did what. Nice to know the book by Legendre. I'll look it up.
I can show the figures if you want. I have them here. Yeah. If I don't know, the organizer can allow me.
Yeah.
Annette.
I have to authorize you. Wait a minute. Yes, Alan. Maybe you can share now.
Okay. Okay. Select. Not this one, probably.
It's coming.
Another one. I made a mistake. It's not the one I wanted to. Or the screen, full screen, I don't know. But no. I should share again. It doesn't work. Okay. Okay. Here, can you see?
Not yet.
No.
It's loading. It's loading. Oh, yeah.
Yes.
Okay, so here you see my row, I don't know. This one is figure 8.
Mm-hmm.
Yes.
This one, break, this one is break orbit, I think.
Yeah.
I don't know where is the collision, but there is collision in the book, at least. It's not numerical. Generally, it's illustration of computation with elliptical functions. So, okay.
Yeah.
Thank
Thank you.
you.
Thank you.
Other questions? Maybe I have one. When you have this limit on the period for the two fixed center to have lemniscat or circling orbits, so what happens at the limit? You think it's just that the orbit stops being minimizing, or will it disappear?
Oh, they do not disappear.
Yes, they do not disappear. Yeah.
They do not disappear. For example,
Yeah,
like a lemniscate type, if we just consider
it's integrable problem, so you know the orbit.
Yeah, right. They do not disappear. For example, it's just like consider two equal masses. But I have tried numerically that when t gets small, then they are really close. I'm not sure who is smaller, but they are really close. So my estimate is just not good enough, which I can't be sure. But it's just that there are some lemniscate type with action values very, very close to the ejection collision solution.
Thank you.
I have a question.
Please.
Okay, Professor Chen, you mentioned a result that uses the Fibonacci sequence, right?
Yes.
Okay, and I have a question. I'm asking myself about the following. Why the Fibonacci sequence? If you use another second order recurrence, the result will be worse? Or do you understand?
Well, I think that is, in fact, I expect the result to be better than that. But the case we are studying has the restriction that every time we apply the variational method, it has to cross at least two centers. That's the restriction we have. Every time it has to cross at least two centers. So if we have three centers, then we have four intervals, 1, 2, 3, 4. So either we can have something like 1, 3, 1, 4, 2, 4. We can have this kind of sequence. And if we just count the number of such kind of sequences with length L, then it just turns out it's like by coincidence. It's closely related to the Fibonacci sequence. If you count the total number of such kind of allowable sequence, then it turns out to be a Fibonacci sequence. So that's the. I think it's quite interesting finding, but it's just only for the case n equals 3, exactly 3 centers.
I understand. But if the behavior of the center change, maybe you will have another recurrence sequence, right?
Exactly. I think that's the really key point I want to point out for the two-center problem. You see, those other approaches, other previous result about like enclosing two centers, at least 2 centers or 3 centers, for those kind of local deformation argument, it has nothing to do with masses, because the result works for general masses of centers. But I just simply think that it's not possible if we are dealing with 2 centers. And if we want to improve the result for the 3 centers, then there has to be something to do with the masses and separation of those centers. So those previous results, like the Fibonacci sequence or the counting the number of realizable CSG sequences, those results works for all possible masses. But I think that to improve it, or improve it to the 2 center or general 3 center cases, there got to be something to do with the location of centers and their masses. So what I study, what I deal with the 2 center problem, I show that it really has something to do with the masses. In order for the minimization approach to be useful, I have to have some condition on the masses. Yeah. Mm-hmm. So in general, yes. The position of those centers and the masses matters if we want to improve the results.
Okay, thank you, Professor Chen.
Other questions, comments? Or maybe a stupid question, but apart from the Kepler problem, I don't know of a real application of the n-center problem to the real n-body problem. Are there some?
As far as I know, I think that one of them is about like if we have an elliptical orbit, whose a body which is not symmetric, then people have used 2 centers to model this kind of non-symmetric body. That's one application. Another application is for the Coulomb problem, where for example we have 2 proton and 1 electron in that electromagnetic field, moving in that electric field. So that's another case where we have the proton fixed. So that's not really application to the n-body problem, but
no, because it's not a perturbation problem.
Right. Yeah. But as I mentioned, this is a step toward resolving the problem of giving a topological constraint. We begin with the simplest, almost like a toy model, the simplest model where only one body is moving. Yeah. But even that case is non-trivial if we have only purely topological constraint.
Thank you. Other questions, comments, contradictions? No?
Have to go home and study a lot.
Counter examples.
Well,
okay, so if not, thank you very much again.
Thanks for inviting me.
It was a pleasure hearing you again.
My pleasure.
Your pleasure.
Have a good return to Taiwan.
Yeah, sure I will. I'm on sabbatical leave in Beijing.
Oh,
right now.
I see.
Yeah.
You want to pass him from his wife or what?
It's more like this. I'll spend half a year with my daughter. That's it's a lot to sacrifice because when I return to Taiwan, there's still 2 more weeks for quarantine. It's by law. So when I on my way here, 3 weeks, and then back another 2 weeks.
Well, enjoy.
Yep. Well, good luck.
Thanks.
Maybe we'll anyway, we have some. Just a moment. Just a moment. Anete, a gente vai tirar foto
Vai também, depois do aviso.
Ah, deixa eu trocar aqui. We will sorry, I need to use Google Translator. I'm not thinking well.
Take a picture now.
No.
Okay, good idea. I will to stop to recording so we can take a picture and after Thiago can speak, okay?